My name is Emily McInturf, and this is my video lab report on the physics of extreme sports with rope. The objective of this lab is to analyze the motion of a spring mass system, predict the motion of the spring mass system with Newton's second law using a computational model in VPython, and then use that model to compute the changes in energy of the system in order to test the energy principle. My main result was that the observed data was a good match with the computational model. And after comparing energies of the system, I found that the total change in energy of the system was zero, satisfying the energy principle. The system I am examining is a spring attached to a mass weighing 0.402 kilograms. The initial position of the mass is negative 0.116, negative 0.6440 meters. It starts from rest, so the initial velocity is 0 meters per second. After analyzing the video, I calculated the spring stiffness to be 6.83 newtons per meter by manipulating the period of oscillation equation and solving for K. I then used this value to solve for the relaxed length of the spring, which came out to be 0.123 meters. The two main physics principles used in this lab are Newton's second law and the energy principle. I used Newton's second law to predict the motion of the mass on the spring. First, I calculate the net force, which is the force of gravity plus the force of the spring. The net force is then used to predict the new velocity and the new position at each time step. Next, the energy principle is proven in this lab. The energy principle states that the total energy of the system is equal to the work done on the system by the surroundings. In this case, there are no outside forces doing work on the system, because the spring, mass, and earth are included in the system. Therefore, the total energy of the system, or kinetic energy plus gravitational potential energy plus spring potential energy, is equal to 0. This is the video and tracker. I set the origin at the point where the spring was attached, and the calibration stick was set to the spring's stretched length, or 0.7 meters. I then plotted all position points and saved the X and Y position data in a CSV file, which is later used to compare the observed system and the computational model. Next, I entered the initial conditions into the given Python code. The mass of the block, which is 0.402 kilograms, the initial position of the mass, which was found in tracker, and the initial velocity, which is 0 because the mass starts from rest. This part of the code reads in the CSV file with the tracker position data so that I can compare the model with the observed data. I then entered the gravity constant and the spring stiffness and relaxed length of the spring, which were calculated in an earlier slide. This part of the code calculates the length of the spring at each time interval. I then entered these equations to compute system energies. To calculate the kinetic energy of the spring, I use the equation K equals 1/2 mass times the velocity squared. For the gravitational potential energy, I use the equation mass times the gravitational constant times delta y. And for the potential energy of the spring, I use the equation 1/2 times the spring stiffness times s squared. We next create a loop in order to first predict the motion of the spring mass system using Newton's second law, compare the prediction with the measurements found in tracker, and compute the energy changes to verify the energy principle. We first define the initial energies. Next, we calculate the gravitational force and the spring force, which we calculate using these equations. We then add these two forces together to find the net force. Once I found the net force, I used Newton's second law to predict the new velocity and new position of the mass. I then used the same code as above to make the spring move and update the visual model. Lastly, the kinetic energy, the spring potential energy, and the gravitational potential energy change and need to be recalculated. These calculated changes in energy are then stored and plotted to notice the energy change at each time interval. Here is the model in Python. The red ball represents the data in tracker, and the blue ball is the computational model. You can see they follow the same path. The blue arrow represents the spring force, and the black arrow represents the gravitational force. The graph shows the y positions of the computational model, the blue line, versus the data in tracker, the red line. As you can see, they are close to perfect match, with the red line slightly lagging due to possible drag force in the real-life model. The code also generates a graph showing the changes in energies of the system. The blue line is the kinetic energy, the red line is the spring potential energy, the green line is the gravitational potential energy, and the yellow is the total energy of the system. Note that the changes in spring potential energy and in gravitational potential energy oscillate with the same period, but as the potential energy of the spring increases, the gravitational potential energy decreases, and vice versa. Also note that kinetic energy is both positive and negative, with the kinetic energy oscillating twice as fast as the potential energy. Now I will answer the what does it mean questions. For my model system, the energy principle is satisfied. The work done in the surroundings is equal to the change in energy, but there is no work being done because the mass, spring, and earth are included in the system. Therefore, the total work must be equal to 0. As you can see in the model, the energy principle is satisfied because the yellow line representing the total energy remains at 0. The second what does it mean question asks me to analyze and compare the oscillation periods for the x and y position data. The average period of oscillation for the x position data is 1.63 seconds, and the average period of oscillation for the y data is 1.38 seconds. As you can see, the oscillations differ by 0.25 seconds. This is because the motion of the spring is elliptically shaped and slanted down, causing the object to move at different x and y velocities, making the oscillation different for each direction. This concludes Lab 4. Thanks for watching.